Hi all, back for another round of physics, and well yeah, let's just go at it. Some rotational kinematic examples. Okay, so we've got one up here. A car decelerates at a rate of 7 meters per second squared. If the initial angular speed of the tires is 95 radians per second, how many rotations are completed by the tires, assuming no slipping? Okay. So in other words, we have a situation where, okay, well, there's a car, and I'll just drive my junky little car, big wheels, small car. There we go, and say, here's my initial state. Yeah, let's do this again. So we'll go ahead and draw a car. There's my little automobile. And so here's the initial state. And we'll say, okay, well, when we start looking at the tires, here's the position of the tires. Okay. Now, as it travels down to the end, okay, well, now we have a car way down here. And say that here is the final angular rotation, or the angular position. There we go. Here's the final angular position of the tire. Okay. And the question is how many times does the tire actually go around during this entire process? So how many complete revolutions does it actually to finish? Okay, well, let's go ahead and let's approach this like our kinematics problems. Okay, we're having accelerations, we have speeds, and then we're asked to find rotations, or an angular distance. So let's go ahead and write down all of our stuff. So over here for an initial, say, okay, well, theta naught, what is that equal to? Omega naught. We'll put alpha, put theta final, put omega final, we'll put time. Let's go ahead and let's stick in some of these values. In fact, I've already started omega final. Presumably we actually stopped the car. And theta, question mark. I'll let you go ahead and fill in some of these. Okay. So say our initial, let's set our initial equal to 0. Our omega initial we're given, this is 95 radians per second. And here we have the angular acceleration. Now we note, we'll have to be careful here, we're actually given not an angular acceleration, but a linear one. Okay, so this is a linear acceleration, A. And the question is, how can we relate our angular acceleration to our linear acceleration? You say, I got this. Okay, if you remember from the last video, we said, hey, there's a relationship. If you're rolling with no slipping, for example, so there's the no slipping part, you can say that your acceleration is equal to the radius times your angular acceleration. So we'll just flip it here. Okay, so this must be 7.0 divided by the radius of the wheel, 0.28. Of course, the units on this, if you wanted to, this would be radians per second squared. Okay. So we'll go ahead and get rid of that. Okay. Well, very good. So what we're left to find, since we're asked for how many rotations, we're actually asked for this, right? The angular distance that the wheel undergoes. So let's choose the kinematic equation that doesn't involve time. We don't care how long it takes. So that being said, we look up our handy dandy equations and we say, okay, well, I've got this. What it is, I guess we'll go over here. This would be omega final squared minus omega initial squared equals 2 times the angular acceleration times my change in angular distance. Now we're just off and running like a bale of turtles, right? We have 0 minus 95 squared equals 2 times 7.0 over 0.28 Being careful here, this is a negative, so I failed to mention. Okay, we'll call that a negative. And you're done. Right? We just have to run the magic numbers. Squared divided by 2, and I believe if we actually calculate this out, we get 25. Okay. So, yeah, let's go ahead. 95 divided by 2 divided by 25 times 95. There we go. So I get something like, okay, well, this is equal to theta. So I get a final answer, excuse me, delta theta, the change in angular distance. I get an answer that delta theta is equal to 180.5 radians. Okay. Of course, we have to be careful, right? We're not asked for radians, we're asked for rotations. So the next question you should ask yourself is, how many radians are in one rotation? Survey says 2 pi. So if I want to take this into rotations, say this would be 180 divided by 5, or times 0.5 divided by 2 pi. This would give me the number of either revolutions or rotations. And we're golden. If something like delta theta is equal to, I have 28.7 revolutions. That's it. Of course, you could go further. You could say, for example, here's an additional question that we could ask. How far does car travel? That's an additional question that we could ask. And we have all the information we actually need to do that. In fact, right here, how can we relate a change in angular distance to a change in linear distance? Again, assuming no slipping. Yeah, you got it. Delta x would just be equal to r times delta theta. So for example, you could say, well, okay, that means my distance is equal to 0.28 times 180.5. Uh, 0.28, there we go. What I get is something, I get delta x is equal to 50.5 meters. Of course, if you prefer, you could also do that. You could do that this way. You could take your speed here, your angular speed, and convert it into a translational speed, and you'll find the same answer. You get this guy. Okay, so there's a couple ways to skin this cat if you want. Okay, cool. Let's go on to the next one then. And miracle of magic, here's the next problem. Well, bam! An automobile engine slows down from 3,222 RPM to 1,027 RPM in 9 seconds. Find the average acceleration, angular, and the total number of revolutions completed in a given time. Sweet. We're off and running like a bale of turtles. So the first, actually one of the reasons I included this, let's be careful here. This RPM should sound familiar. This is kind of the thing that you have in what's called the tachometer. So this is like the tachometer in your car, and it stands for revolutions per minute. So it's still it's an angular speed, but the issue is that it's not in your standard SI units. You can take revolutions per minute, and we'll have to actually convert that into radians per second. Okay. So that's one of the things that we have to be careful for, is the units tend not to be standardized as much when you're talking about angular rotation. So just be careful. Know what unit you're actually working in. Okay. Well, so for the first part, let's get an idea here. Of course, it's kind of hard to draw an automobile engine in the initial and final state. But what we'll say is, okay, well, we'll still write down some of these variables that we know. So if we're going to apply, well, here we go. First of all, you notice that we're asked to find the average angular acceleration. Right? What does that mean in the sense of, well, I guess, excuse me. So you notice here, we're asked to find the average angular acceleration. Okay? And the average will be constant, right? That's by definition. Even if the acceleration is changing dramatically, the average is a constant value. Okay, so what we're really dealing with here again is alpha is equal to constant, which means that pings right away that we're going to be using kinematics. Now, it's hard to draw like an initial final state here. I mean, drawing an automobile engine, and you get what I'm saying. But we can still list out everything that we know and what we need to find. So let's say we have theta naught, we have omega naught, we have alpha, we have theta final, we have omega final, we have time. Let you fill those in for a second. Okay. Well, of course, time, we're given 9 seconds here. And our omega final, again, we have to convert from revolutions per minute to radians. So the revolutions to radians, 1 revolution is 2 pi radians. Okay? So we have to multiply this number by 2 pi, so that's the first thing. So we have 1027 times 2 pi. And then minutes to seconds, well, you've got that. There's a 60 in here, so that's 60. And whatever that value is, that'll be the radians per second. Of course, we don't know what this is. We have this. Don't know what the angular acceleration is. And the initial speed, we'll use the same kind of idea, 322. Okay, those are revolutions. Each revolution has 2 pi radians. And that all occurs in 60 seconds. Okay. So the first question asks for the angular acceleration. So I need to choose the equation, the kinematic equation, that doesn't involve the final angle, theta final. Give you a second there. Got it? Well, here we go. I'll go ahead, write down average, and sometimes the average is the helpful part too. Just going to use this. Right, the definition of angular acceleration. Well, let's go ahead. Actually, yeah, so here we go. We get equals, well, this is 1 over 9 seconds. And what I'll do is I have 1027 minus 3222. And that quantity multiplied by 2 pi over 60. Right? And go. Say, who can calculate it out faster? So I get something like negative 25.5 radians per second squared. And there's my value of alpha. Total number of revolutions completed? Well, okay. I guess probably the easiest way to do that is let's find the equation that does not involve the angular acceleration. All right, let's see if we can, since we're after this theta final, let's see if we can find the equation that doesn't involve the angular acceleration. Got it? Good. Well, this will actually, I guess this will be 2 of them. What I'm going to do is I'm going to start off with, well, let's use our definition of angular speed. That would be delta theta over delta time. And then substituting in right here, I'll use that mathematical expression for average, the arithmetic average. So I have W naught. Be careful, this is not a delta. This is an average, so I'll put plus W final over 2 equals our change in theta over our change in time. Or, well, at this point we can sub in values. Yeah. Okay. So what we have is, yeah, here we go. I'll put 1027 plus 3222 divided by 2 times, of course, 60. And this top should be multiplied by 2 pi. And then you should also multiply by the time. Equals our change in theta. Yeah. So let's go ahead, let's run the numbers there. So I got something that said, hey, my angular distance is 2002 radians. And of course, we go back and we say, hey, wait a minute, we actually want revolutions, so I got to convert that back. Nah, that's not too hard. I've got a conversion factor, 2 pi. So at the end of the day, and I'm sorry, I'm running out of space. Oh, goodness me. Sorry, I wasn't thinking about that. Let's shift that up a little bit. So at the end of the day, what I have is I got 318, depending on how many decimal points you want to keep, I'll say 0.7 revolutions equals my change in theta. So there's our two answers again. Okay. I'll see if I can dig out some more, but that's just a couple of really quick and easy examples of just using the kinematic equations for rotational motion. Of course, we'll have a couple more involved when we incorporate, say, for example, forces or torques or energy. Just a little teaser to kind of get our thought process going for the conceptualization. So I thank you for your time. I'll see you next time.